Thank you, Justin. Thank you, Sadvana, and thank you, Remy, for this invitation and nice meeting. So I will, the whole talk is about the NLS equation with power nonlinearity. Usually the dimension is any dimension, and nonlinearity is just energy subcritical. So this was mentioned already that this dimension 1 and cubic NLS is integrable. Here I mentioned Geneva and Velo because well, I'm concerned with H1 solution. Anytime I say I have a solution, it's an H1 solution. So it's defined in the energy space H1. So I record here the mass and the energy. Well, I didn't put the momentum. Now here I recall quickly what I mean by solitary waves. So all what I do is based on the ground state Q, positive radially symmetric solution of this equation. I just record this explicit decay at infinity. So it's exponentially decaying with a polynomial, well, a power perturbation. And then I have this rescaling law. So I define the Q omega. And then what is very well known is that with these parameters here, the phase, scaling, position, and speed, we generate this family of explicit solitary waves. Whereas are indeed explicit in dimension 1, not really explicit in higher dimension. Existence is due to several papers. Here I mention Berestik-Ilians, Kwong for the uniqueness. It's very well known that a single wave is stable if and only if P is subcritical. And here I mean L2 subcritical. This is L2 critical exponent here. Fine, so this is all well known. Now I will look for a solution containing more than one soliton. So I take any such soliton for any parameters, speed and scaling and position and phase, and I define this Rk, right, in the same way as before. And this slide is concerned with this case when the speeds are all different. Okay? Then because of the exponential decay here, of course the wave will be very decoupled as time goes on, for large time at least. And then what happens is that you can construct a solution which is asymptotically, for large time, the sum of such Rk in H1. This is H1 of R, in the H1 topology. And this difference is exponentially small in time as time is large. So that's kind of natural because the nonlinear interaction between waves is indeed exponentially small in time for large time. So that's quite natural. So here you have three references because the L2 critical case was treated by Mayer as a byproduct of a blow-up result. I will speak about it just after. The subcritical case we treated first with Frank, and the supercritical case, because of the instability of the wave, we need one extra argument to control the instability. But since the instability is very well known, it's only one-dimensional exponential instability for each soliton, it's not hard to control it. Just to make a construction, here there exists one solution, right? It's not just a construction of one specific solution like this. So a few comments. Of course, in the integrable case, this multi-soliton are known. So as everyone I mentioned, the Sakharov-Shabbat work. And in fact, they are much more special than what I said. because they are also multi-soliton at minus infinity in time, and they do describe the pure interactions between solitons. So they are much more than asymptotically multi-soliton. They are multi-soliton, I would say, in the sharper sense. Stability and asymptotic stability of such object in the integral case is known by Kuchania and Pelinovsky in some weighted L2 space. Similar results of existence of asymptotic multi-soliton are known for other models. So for the generalized KdV equation, we have paper with Tsai and another paper here. And the supercritical case is treated here and here. And also we have similar results for the Kamasa-Hom equation by Eldika and Molinet, and for the Gross-Petersky equation, etc. So, in the non-integrable case, the solutions that are multi-solitons asymptotically for t go to plus infinity are not expected to be multi-soliton as t go to minus infinity. Because of course, when you go backwards in time, you expect to have nonlinear interaction that kill the structures that you have asymptotically. And Galina Perelman published a paper where she studied for perturbation of the cubic case. She studies the interaction of a large and a small soliton and proves that the small soliton should split. I mean, it splits, actually. And we did something similar with Frank Mer for KdV, studying the collision of two solitons for a big and a small soliton. This is one of. And there is also work with, of Claudio Munoz. And the outcome of these works is that whenever you work with a KdV equation which is not completely integrable, then at least you have a defect in the collision, meaning that the solution which is a multi-soliton at plus infinity definitely is not a multi-soliton as t go to minus infinity. So there is always a defect in the collision if and only if you're not working with the integrable KdV. So for NLS, so to my knowledge, there is only this work so far. Here I just mentioned a word on the proof. So the proof is based on kind of soft energy type arguments. It could also be done probably by fixed point arguments because of the exponential decay. But you do need to have some spectral properties of solitary waves. You don't exactly need that the solitary waves are stable because we can manage the unstable case. But at least you need to understand all the instability direction to do that. And it is not always the case, especially for bound states, that is for excited states. So it's mainly open for this. For the Klein-Gordon equation, there is also such construction by Cotte and Munoz. And with Cotte, we could manage the case of any bound state. Because for some structural reason, it's easier. So we can treat any bound state here. Okay, so now I will speak about, so I told you, so I go backwards here. This slide was concerned with different speeds, right? I will try to do same speed. I would like to mention this result by Tien Vinh Nguyen. So I work here with, so I take the subcritical or the supercritical, but not the L2 critical. I will go back to this critical case just after. There exists a solution which is exactly the sum of two solitons with the same size. Q is just Q with scaling 1. Of course, you can rescale the result. So you have a phase, and you have two positions, so Z1, Z2. And in fact, they are symmetric. Z1 is minus Z2. And the distance of the two solitons is just 2 log of t. And you have this error term, so it's not anymore exponential, as I will explain. So the solitons here are quite close. They are log close, and they decay exponentially. So interaction will be power-like in time. And this, so here you have no restriction on the dimension, no restriction on the P, except that you don't want to have the L2 critical P. I will explain why. So again, in the integrable case, this was known already. They are called the double pole solutions. They are already contained in this work, with some more detail in that one. And again, in the integrable case, these double pole solitons are much more special than just asymptotical. They describe also pure interaction of solitary waves. In this result, it's necessary that the two solitons have the same scaling. So you need this. You need to match the same scaling and the same phase, right? And the solution has space symmetry. So this I said already. The interaction between the two solitons are no longer exponential in time, and you have power-like errors. So you need to compute a little bit an ansatz, which is a bit more refined than in the other case. It's a bit harder than the exponential case. Especially this case, when you take close to linear nonlinearity, it's even harder because of the nature of the interaction terms. When you Taylor expand the nonlinearity with a sum, it's a little bit more difficult in this case. So Tien Vinh Nguyen also proves the same result for KdV. So for KdV, any nonlinearity except the L2 critical one, you can prove the existence of two solitons that split as log in time. So the same result. So I guess all this was expected somehow, but so now we have proof, right? Okay, so I just, why it was expected that the formal law is not simple to guess, and it was already somewhere in the literature for formal argument for that. So there is a technical thing that you need to rescale, but this is not too bad. So you need to rescale the equation a little bit, but let's forget about it. So essentially you consider the Schrödinger equation like this, and you make an ansatz which is the sum of two pk. So it's not exactly the rk because I adjust slightly. I have to tune a little bit the position and the speed, and I have tuned already the scaling here. I have tuned the phase, and the phase and the scaling are tuned in the same way for the two solitons, unlike, of course, the position and the speed that are opposite. This quantity are, you see, you have a certain symmetry. Okay, so if I put this sum into the equation, well, I find such equation for each of the pk. So it is the Schrödinger equation for pk, of course. Then I have a term coming from the z dot. I have term coming from the v dot, and all of the terms are not so relevant, so I forget about them. And of course, I have the nonlinear interaction. Of course, I mean the sum of a solution is not a solution. So I have here a difference between these two, right? So we need to compute it. So we write this difference. So this is a nonlinear interaction term. But it happens that at least if p is bigger than 2, it's not hard to compute it by Taylor expansion, right? It's easy. And once you are on P1, for example, you are on P1 and you look at the asymptotic of the P2, it depends on the asymptotic of the soliton itself, which is well known, right? So it's not hard to look at the interaction of the distant soliton on the soliton 1. That's not hard. And if you do this and you project, if you project this equation on the nice directions that are related to this direction here, you obtain the equation for the parameters. And so I insist on important terms. So of course you have interaction everywhere, but some are important and some are not. So this one is important. So this interaction here will definitely change the v dot. And if you forget about this term, which is not relevant, and you combine these two, you have a second order equation for z, which is very simple. You have z dot dot is equal to this with a 2, right? And c is positive. C is positive if and only if I take two solitons with the same sign and same phase. If I change the sign of the phase, I will get something different. And if I look at the equation z dot dot is equal to this nonlinearity, you have the solution like T, the one of the first theorem, and then you have a solution with log. Right? It's an exceptional solution. It's kind of unstable, but you do have this kind of solution. It's very easy to be convinced by this. This solution is, so this is a slightly more precise information on that one. So at the end of the day, the behavior of Z is like that, with the constant C is the same here. So formally, it's not hard to see that there is some exceptional solution, at least on the ODE point of view, right? So that's not hard. So what you need to do next is to control the error term, which is an infinite dimensional guy, and for this you need to do something which is reminiscent from Weinstein's method to prove stability. So, except that you have two solitons. So
yeah, I lost track of the notations.
Oh.
But he said
Z is the position and V is the speed. Right here.
And the phase, gamma is just.
The phase is the same for the two solitons. So, well, yes, they are tuned. The two solitons are tuned somehow. They have the same phase, same scaling. And what is opposite is the position and the speed. They go, you see, it's very symmetric. So in fact, if you write one equation, you have the full thing, because it's very symmetric. Okay, so at the end, you have the equation for the position is Z dot dot is equal to this nonlinearity. So it depends very lightly on the dimension, as you say. It depends a little bit on the dimension, but here it does not depend on the dimension. At least at the leading of the term does not depend on the dimension. Well, and he did it for two solitons, but you can do it for many, and you have to put the soliton on a polygon, a regular polygon. That works the same. But you need a lot of symmetries. Right? Okay, so, okay. Yes, okay, so this was the subcritical case and the supercritical case as well. For the critical case, something is wrong here, and it's easy to see. So now I look at the L2 critical case, and for simplicity, I will look at the cubic in 2 dimensions, which is indeed L2 critical. So the first remark is that such a solution cannot exist for the L2 critical case, because in the L2 critical case, you have the Virier identity that says that this quantity here is a polynomial of order 2 of the time, right? Because this identity. And then you cannot have such a thing as 2 solitons and only 2 solitons moving on log t trajectories, because then this is, you can say that x of t, you can put it outside, like the position z of t, and so you get that this quantity is log of t squared time a constant, and that's not possible. You cannot have log of t for a quantity whose second derivative is exactly a constant, right? So you cannot have such solution for the critical case, so that's hopeless. Okay, so what you find instead, so you still have a solution, right? But it's different. So this is the way it goes. So here we did it for k, just for, okay. So you take, so it's an existence result again, right? It's a construction. We construct a special solution. So, and here again we have a lot of symmetries, right? So you take Q, the one of the critical case, and you rescale it. This is a L2 critical scaling for 2-dimensional case. You have the same scaling, same phase for the 2 solitons. They are tuned. Of course, the positions are different, but the zk go to the vertices of a regular polygon. Okay, that's very symmetric. So if you take 2, you have just the previous situation. And you have a solution like this, but so as you see, the positions are fixed. So they are finite distance, but the log is to be found in the concentration. So the soliton concentrate, and that ensure somehow the decoupling. So in a subcritical case, you have decoupling because they go away the one from the other with the log. In the critical case, they stay at finite distance, but they concentrate as a log, and that somehow has the same influence on the interaction. The interaction is still not weak, but polynomial in time, so it's perturbative, right? So you can do analysis because it's perturbative. And if you compute the gradient in L2, you find that it's exactly this. So you find what you can call a blow up in infinite time. It's a global solution, but it concentrates and the gradient goes as a log. Okay? So what's the difference with respect to the subcritical case? For the subcritical case, I told you that the main influence of the interaction is on the speed, and then it transmits to the position by the equations. Here, the main influence of the interaction is not on the position, it is on the scaling. That is the first. If you write the full system, I won't do it, but if you write the full system of all the parameters, well, the scaling has to move, and the scaling is perturbed exactly by another law, and somehow the perturbation is not relevant on the position, it is relevant on the scaling. So you have a scaling instability which is damped by the interaction of the two solitons. Another observation that, of course, such a solution cannot exist for the subcritical case where all solutions are global and bounded, but for the supercritical case you could expect unbounded solutions. But you cannot have, because if you write the Via identity for the supercritical case, you get an extra bit of gradient here, and if you integrate twice, you prove that the gradient, at least on a subsequence, has to be bounded in time. And this one is not bounded in time. So you cannot have such, so it's really exceptional to the critical case. And I think it's very similar to the other case, but you have this scaling, behavior. Okay, so now what I will do, I will review briefly the blow-up problem for the L2 critical NLS, and I will write the consequence of the previous theorem on blow-up, because this cannot be considered really as blow-up, right? It's a global existence, and you have concentration in large time, but this has a consequence that some of you already computed, maybe by the pseudo-conformal transform. It has a consequence on finite blow-up, finite time blow-up. So I first, before doing that, I will review a little bit blow-up problem for NLS. So this was recalled already, the famous Weinstein result that for any data small enough, that is strictly smaller than the soliton in L2, the corresponding solution is global and bounded. Then we have that in addition, if U naught is, so you have the following improvement that if U naught is just in L2 and smaller than the threshold, that not only the solution is global, but it scatters, that is, behave linearly as time goes to infinity. And this was a radial case, and this is a general case. So we know pretty well the solution in that case. Now, for the threshold, this was already in a couple of talks, but you can do the pseudo-conformal symmetry on this explicit solution, and you find the solution S. It blows up where you want. You just fix a capital T, and it blows up at capital T if you wish. And it has this following blow-up rate, which I will call the conformal blow-up rate, and it is minimal mass. And Frank Merle proved that this solution is the only one that blows up with this amount of mass in H1. Good. So now if you go slightly above the threshold, there were papers by Galina Perelman and Merle and Raphaël. And the theorem as stated is due to Merle and Raphaël. You can find an open set of initial data, including negative and zero energy function close to Q, which lead to blow up with the log-log speed, which was long conjecture. For example, you have this Landman, Papa Nicolaou, Sulem, and Sulem reference, which was speaking about it. Okay, and such a solution concentrates the mass of Q at a point in L2. In the following sense, plus a residue which is a function in L2. This is a Dirac mass at a point. So, so what I want to remember from this slide is the fact that you have solution, and in fact it is called the stable blow up. You have solution which blow up with square root of log-log over t, right? This is called the log-log law, okay? So it's pretty different from the conformal law, right? It's very different. This one is much closer to the...
This result was obtained first time by Freiman, it seems to me.
Right.
You know, the Freiman from 1987.
Okay, fine.
Something like that. Yeah. And then it was repeated on the physical level of
right.
times. So probably that was the first mathematically rigorous result. But anyway, the formula was known for decades.
Yes, that's right. Okay, so if we still look for solution close to Q, right? Solution close to Q, Pierre Raphaël proved that you have a gap. I said that there are two blow-up regimes, the log-log one and the conformal one, which are very different. And what Pierre proved is that you have a gap, that is, you cannot reach any blow-up rate in between, right? So you can reach the log-log, you can have t minus t to the minus 1 and above, maybe, but nothing in between, okay? But this is only for solution close to Q. Apart from this result, there have been, and Gadi Fibic talked about this earlier, other conformal blow-up solution constructed by Boga and Wang as perturbation of the solution S. They take the solution S and they perturb it far from the blow-up. This was in some dimension, and Krieger-Schlatt did it in dimension 1, I think. And Mel, Raphaël, Scheftel proved some instability result, and I should add the Gadi reference here, probably. But so far it's an open problem to prove whether or not there exist other blow-up rates for NLS. We have log-log, we have 1 blow-up, but we don't know whether there exist other blow-up rates, right? Well, there have been attempts to do other blow-up rate by changing the equation. So it's a little bit of cheating, but why not? So, so this attempt was it's a very nice paper. It's kind of unlucky because if you perturb the equation, putting a potential here, with this condition, the potential is kind of non-degenerate at 0, right? It's flat, but not too flat, right? Then you could expect a different blow-up rate, maybe, for the minimal mass solution, but it does not happen. So you find the same blow-up rate. There is a cancellation in the paper, which is kind of unlucky. This paper is related to well, non-existence of blow-up, and this one is related to the same question with 0 here. So all these papers are very complementary. Okay, so we have made with Stéphane Locos and Pierre Raphaël another attempt to change the equation, and this attempt has been a bit more lucky. If you take the cubic, so this is L2 critical nonlinearity. If you perturb the equation by a subcritical nonlinearity, very surprisingly, you find a blow-up rate for the minimal mass solution which change, and the more P is close to the critical one, the more the rate is different from the conformal one. It seems kind of weird, but well, it's not continuous, right? Well. When p goes to linear, so when p goes to 1, then you find the conformal rate. And that makes sense. A linear perturbation is nothing. A nonlinear perturbation can have a lot of consequences. And this is because we look at the minimal mass, right? If you look at log-log, still exists. The log-log rate is much stable, is very stable. And so it wouldn't be affected by this small perturbation. But minimal Brob solutions are affected by a nonlinear perturbation like this. If you put a minus sign here, you find no minimal mass Brob solution. So you have to put a plus. Okay. So what next? So if we go far from the single soliton case, so several soliton case, so as I told you, so this is the same result as before for Frank. In the whole space, he could prove the existence of a solution that behave the sum of solution S at finite distance. And if you do the conformal transform, you find solution which is global, and it is a multi-soliton at infinity, right? So so if you take just this solution, okay, so this go to infinity, you make the conformal transform, you find S of t, which is the peak Brob solution, right? Now, if you look at of a solution like this for large time, and you make the pseudo-conformal transform, you find, right, and this is 1. And so you find, so here you have distance like t at infinity, and this is, say, at t go to capital T. Okay, so this is the well-known result of existence of a Brob solution with minimal mass. And this is Frank's result, right? Both sides are in the paper. So if you take a multi-soliton at infinity, like this, and you make the conformal transform, you find a solution that blows up at k different points, but with finite distance, non-zero distance. Okay? So here I wrote the consequence of the existence of a log solution once you do the conformal transform. Okay? So our solution with the log is something like this. Well, I don't want them to move necessarily, but I want the distance, let's say it could be like this, for example. Okay, so log solution is like that. Distance is 1. So this is t go to + infinity, and this is like log of t. So the size here is log of t. Okay, this is our result with Pierre, that we construct a solution which is the sum of two solitons, finite distance at infinity, and the size is log. Okay, so if you do the conformal transform of this, you find peaks that will collide at a point. And the size is log of t over t. Right? So, so it's just a consequence of the other theorem. You find a solution which concentrates k soliton at a point, so it's a collision at a time, a finite time, and the Brob rate is slightly, very slightly above the conformal one. So you find a log modification of the conformal Brob. So it's a first example of something different than the conformal Brob and log-log Brob. It does not contradict Raphaël gap for two reasons. First, we are not applying, we cannot apply Raphaël result because we are not close to Q. We have two solitons. And second, it's above 1 over t, so we are not in the gap, right? So, of course, no contradiction. Okay, what else? Well, I'm done. Actually, I put a couple of slides with many references. So we're not the only one to work with multi-soliton, of course, and with blow-up rates. Let me mention exotic blow-up rates is a very active field. And I think one of the best on the earliest reference is Krieger, Schlag, and Tataru, who proved the existence of exotic blow-up rates, a continuum of blow-up rates, actually, for some wave equations. In the energy critical situation, rather, well, I won't comment on all these papers, I guess. Well, I just like to mention Mizumachi results, which this result is for the quartic KdV equation, non-integrable equation. It could prove that the interaction of two solitons of the same sign is repulsive. Right? So it's a case of strong interaction between waves as well. So this is why I like to mention it. You also have a similar result for parabolic equation. This Herrero-Velasquez result is also related to collision of two bumps. So you have blow up with the collision of two bumps, and they obtain, in this way, they obtain a different blow up rate as well. So that's also interesting, but it's a heat equation, it's a different equation, of course. Okay, so I will just stop here. Thank you very much.